Energetics 1. Measuring energy changes, exothermic and endothermic reactions. Reactions involve energy changes. Physical changes such as melting and condensation either absorb or release energy. You can see here that melting, when a solid turns to a liquid, energy is absorbed. Conversely, during condensation, when a gas converts into a liquid, then energy is released. In chemical changes, similarly, say photosynthesis, for example, when we turn carbon dioxide and water into glucose and oxygen, energy is absorbed for this during this chemical reaction. Conversely, oxidation reactions release energy. So, what happens in a reaction? Well, first of all, we know that we have a reactant converting into a product. And we've got this example here. We've got water being converted into hydrogen gas and oxygen gas. And here we have a pictorial representation of it. The red circle is oxygen. The two little white circles are hydrogen. And you can see there's a bond between hydrogen and oxygen. So in the reactants, we have 2 water molecules. And we have 1, 2, 3, 4 bonds altogether. Bonds in the reactants break during a chemical reaction. And you can see here that the oxygen and the hydrogens are no longer bonded, as before they get converted into the products. In the products, there's a new bond formed between the hydrogen and the hydrogen, and the double bond between the oxygen and the oxygen. Energy is used to break these bonds in the reactants, and energy is released when forming these bonds. And overall energy change of a reaction is to do with the amount of energy used here and the amount of energy released here. All reactions use and release energy. Let's look at endothermic reactions first. We have reactants converting to products. We've got the energy used to break the bonds and the energy released to form new bonds. If the energy used to break bonds is greater than the energy released, then energy is absorbed overall, and we have an endothermic reaction. Conversely, in exothermic reactions, we're going to use energy to break bonds in the reactants, and we're going to release energy as the bonds form. But if the energy released is greater than the energy used, then energy is released overall, and it's an exothermic reaction. We like to think of this as systems versus surroundings. Okay? Energy is transferred between a system and its surroundings. The system is the chemicals in the reaction. You can see here, it would be within this liquid, would be the system. The surroundings is everything else around that system. The law of conservation of energy states that the total energy is conserved in chemical reactions. So the change in energy of the system must equal the change in energy of the surroundings. Let's have a look at system versus surroundings in endothermic reactions. Energy is transferred from the surroundings to the system. So you can see here the surroundings is transferring energy into the system. Energy is absorbed by the system. Energy is lost by the surroundings. So the temperature of the surroundings decreases. So in an endothermic reaction, the temperature of surroundings decreases. Oops. A good example of this is a coal pack. The system here would be the chemicals within the coal pack, and the surroundings are the air and indeed the arm in which the coal pack is on. So heat from the arm will transfer into the system, and that will cool down your arm. Here, system versus surroundings is exothermic reactions. Energy is transferred from the system to the surroundings. So energy goes from the system, the liquid in this case, to the surroundings, which would be air in this case. Energy is released by the system. Energy is gained by the surroundings. So the temperature of the surroundings increases. Over here you see a candle. The system is the wax that's being drawn up in a thread. And the surroundings is the air. So energy from that wax, once it's undergoing a combustion reaction, is being transferred into the air. Examples of endothermic and exothermic reactions. State changes, evaporation and melting are endothermic. Exothermic. Condensation and solidification are exothermic. Exothermic, we have combustion reactions. And this is quite an easy one because obviously things are heating up when something is being combusted. A lot of heat's given off. And neutralization reactions between an acid and a base. These are quite common reactions. Less common, I suppose, are the endothermic ones, and some examples I could give are the thermal decomposition and cracking of alkanes, which is just the splitting of alkanes. Enthalpy is the heat content of a substance. Enthalpy is the heat content of a substance. And it's basically the total internal energy of a substance, which will include the potential energy, which is stored in the chemical bonds, and the kinetic energy, which is due to motion. The symbol is H. Just give me a minute. Capital H. And the units are joules or kilojoules. The absolute enthalpy values for any given substance can't be measured. Okay, you can't measure an absolute value of enthalpy, but you can measure enthalpy change. And that would be, the enthalpy change reaction would be the enthalpy of the products minus the enthalpy of the reactants. You can see here an enthalpy diagram, and you'll become very accustomed to these things, okay? You've got kind of time along the bottom, which is written as reaction progress. You have enthalpy on the y-axis. For an endothermic reaction, energy is absorbed. The enthalpy of the products is greater than the enthalpy of the reactants. So you'd have reactants lower down on the y-axis because the enthalpy of the reactants is smaller or lower than the enthalpy of the products. The products would go higher up. And the difference between the two levels would be the enthalpy change. Okay, that's the enthalpy of the products, subtract the enthalpy of reactants. And in this case, obviously, it's a positive delta H. In exothermic reactions, energy is released. The enthalpy of the products is less than the enthalpy of the reactants. So if we put that in, you see reactants would obviously be above the products. And you can see the enthalpy change there is negative. So we have negative delta H. Thermochemical equations. We're going to have a look at a few examples here. The enthalpy change can be included in a balanced chemical equation. So when 1 mole of water vaporizes, 45 kilojoules of heat energy are absorbed. You can see here, we've got water plus 45 kilojoules of heat will give us water vapor or gas. The energy here is being treated as a reactant. It's being absorbed, and therefore it's endothermic reaction. We also would write it like this. This would be the common way of writing it. You'd have your reaction, and then you say after the reaction what the enthalpy change is. And you can see positive means endothermic. Example 2. When 1 mole of methane undergoes complete combustion, 75 kilojoules of heat energy are released. You can see here, 75 kilojoules is one of the products of this combustion reaction. If it's a product, it's being released, therefore it's exothermic. Obviously we can write it like this, and delta H would be negative 75 kilojoules moles. Negative exothermic. Standard enthalpy changes. You can see we've got a little TIE fighter written in the top right of the delta H. And this means it is measured under standard conditions. That symbol there means it's measured under standard conditions. And the pressure would be 1 times 10 to the 5 pascals or 100 kilopascals. A molar concentration of aqueous solutions is 1 moles per decimeter cubed. And all substances are in their standard state. The standard state is the normal, most pure stable state of a substance measured at 100 kilopascals. And temperature is not included in the definition of standard conditions, but 290 Kelvin is often given. The energy term in a thermochemical equation is part of the balanced equation. You can see here that you relate this energy change to the amount in moles used in the reaction. So 1 mole of oxygen gas in this reaction, reacting with 2 moles of hydrogen gas, gives us 2 moles of water vapor, and that would be an exothermic reaction with 492 kilojoules. Okay, so this figure is associated with the molarity here. If you wanted to rewrite the equation to show the formation of 1 mole of water vapor and its enthalpy change, we would need to half everything. So we'd half that to get 1 mole. If you half that, obviously we know our molar ratios from stoichiometry. So you get half oxygen, you'd get just 1 hydrogen, and then you'd need to half this too. Okay, so half of 492 is minus 246 kilojoules. So it's quite straightforward. Example 3. The thermochemical equation for the standard combustion of ethanol is as follows. If we need to calculate the heat released when 0.25 moles of ethanol burns, we need to look at the ratios. We've got 1 mole of ethanol in the balanced equation, and we want to know 0.25 moles in the question. And so we could use a conversion factor. We know minus 1367 kilojoules is for 1 mole, because we've got 1 mole of ethanol and we've got minus 1367 kilojoules moles given here. So conversion factor, okay, we're trying to work out the heat release, so joules will go on the top and cancel moles, and will give us minus 342 kilojoules, and we need to convert that to 2 significant figures. Example 3. The thermochemical equation for the standard combustion of ethanol is as follows. Calculate the heat release when 2 grams of ethanol burns. It'll be a 2-step procedure. First, we'll find the moles of the substance in question, and we'll do that using the molecular mass. And we use a conversion factor of 1 mole is 46.08 to find the moles of ethanol. And then once we've got the moles of ethanol, we can calculate the heat released, because we know that 1 mole gives us 1367 kilojoules, so we can use this conversion factor to find out how much heat 0.0434 moles would give us. We get minus 59.3. Example 4. When 4 grams of sulfur are burned in excess oxygen, 40 kilojoules of heat is evolved. Calculate the enthalpy change for the combustion of sulfur. Well, we've got 1 mole of sulfur reacting with 1 mole of oxygen gas to give us 1 mole of sulfur dioxide. To find the moles of the substance in the question, we convert grams to moles using the conversion factor of the molecular mass, and to get 0.125 moles. The heat for 1 mole is going to be 40 kilojoules over 0.125 moles. So 1 mole will be 40 over 0.25, and get 320 kilojoules. And we've got to convert to 2 sig figs because of the question. And so it's a combustion reaction. We know combustion reactions are exothermic, so it will be minus 3.2 times 10 to the 2 kilojoules per mole. Example 5. The molar enthalpy of combustion of methane is minus 75 kilojoules per mole. What mass of methane is needed to produce 1.5 times 10 to the 5 kilojoules? We know that 1 mole of methane gives us minus 75 kilojoules per mole exothermic reaction. So first we need to find the moles of the substance needed. We know that 1.5 times 10 to the 5 kilojoules is produced. We know that 1 mole gives us minus 75, so we use this conversion factor to find out the moles of the substance needed. It's going to give us 2 times 10 to the 3. Then we're going to find the mass required. We've got the moles, so we can just use the conversion factor of the molecular mass of methane to give us our final result in grams. And that's it for this presentation. Splendid.